Hello everybody, and welcome back to my homework 1, Vectorization, Jacobian, Frenet-Serret, plotting, redo. This time I'm going to be looking at part 2, using closure, explain and code a higher order function that returns functions that calculate the Frenet-Serret tangent and normal vectors for the helical curve, which I generated last time. Explain how radius curvature can be obtained at any point along the helical curve. Awesome. So there's a lot to unpack here, and let me go ahead and start out by unpacking it in maybe a drawing. So we have this helical curve right here, right? And our end goal is to generate a bunch of these orange circles around the helical curve and then connect them all. So let's say at any point along the helical curve, say right here, I want to know the tangent and normal vectors. And you see, why would I want to know those? Well, I'll get into that in a minute. But let's say I want to know the tangent and normal vectors. So just approximately, what do those look like in this situation? Well, the tangent is going to look like this, right? I guess I shouldn't draw it on both sides, but we'll just say the tangent kind of looks like this. It's a line that only intersects the curve at one point. And the normal vector is actually going to point inside towards the middle of this curve, sort of like the center of the circle, if you will. And if this were a perfect circle, sorry, there's a fly kind of getting in my face. Maybe more of a gnat, I don't know. But anyway, this is pointing directly towards the center of the spiral. This is sort of the normal, so I'll go ahead and label that as the normal, and that's the tangent vector. And if you look at these two vectors, they are just the two derivatives. So like this would be df over dt, and the normal vector is just the df squared. No, it's d squared f over dt squared. I think I always kind of forget where the squared should be when you do second derivatives and so on and so forth. But I think I got it correct this time. Anyway, I'm looking at, so this is like the tangent normal vectors, and the whole reason I'm generating these is because I can take the cross product of these two vectors and get a vector b, which is always perpendicular to the curve. So this b is always perpendicular to the curve, and then there's a plane created by the product of b and n. So b and n make a plane. And this plane is where we can plot all these orange circles. So I could take that one, I could take that one, I could take this one, I could take any of these, and this is why I'm sort of trying to find the tangent and normal vectors. So let's go ahead and maybe take a look at Mr. Wikipedia. Or Miss Wikipedia, I guess. I don't know. Maybe Wikipedia's gender neutral. I don't know. But I think I'm going to go with, I don't know. So anyway, here's a better illustration of the vectors I was talking about earlier. Here's the tangent, or the first derivative of the curve. Here's the normal, or the second derivative of the curve. And then here is b, the product of these two vectors. And the binomial unit vector, the cross product specifically. Thank you, Wikipedia, for helping me out there. So then Frenet-Serret is saying that you don't just need the unit vector, or you don't just need the vectors tangent to the curve. You need the unit vectors tangent to the curve. And the unit vector is actually this vector t derived relative to s. And what is s? Well, s is the arc length, if I find it. Yeah, okay. So it's arc length. So arc length is just, you can see that little graphic. That's just the angle, sort of the angle that the curve is at along its rotation, right? So I didn't mean to click on that. Yeah, awesome. Let's go back here, review the code real quick. I'm going to define a Frenet-Serret function. I'm going to then take the change in the function over time, use that to get the tangent and normal. I'm actually going to have to divide this by this arc length parameter, and I'll get back to that. And then that'll let me get two functions. I can define however I want, and then call the magnitude, or like the unit vectors of tangent and norm, and that'll be useful for when I'm trying to go forward and yeah, you find like the radius curvature, because this will give me a plane at any given point along the curve, which is sort of what I'm looking for. So with that, let me go ahead and clear these two cells out. And let's go ahead and get started on programming the Frenet-Serret. So I'm going to maybe say that I want to create this Frenet-Serret function. I want to give it just a function. I'm going to give it a function, and it's going to return to me two functions based on whatever function I give it. And then I want to return a tangent function and also a normal function, which I'll just abbreviate as tangent and norm. So I need to define these functions. So I'll define tangent in terms of t. I want to take the derivative. I want to get the tangent function at any point of t along the rotation. So or any time, essentially, I guess. T is sort of time. It's sort of like a measure of the angle I'm at. It kind of depends on how you want to think about it. I'll call it time, and maybe imagine that this is like being plotted over a certain point in time and all that sort of stuff. So I've defined tangent, and I need to return some sort of array that I'll just call t. Or no, I can't call it t now, can I? Because that's the same thing as this t. Maybe I will just call it tan. I don't know. And then I will also define a normal function at any point t, and that will just return to me this like normal vector. So, and I'm kind of reusing some variable names, which I don't love doing, but you know, whatever. So how do I get this Frenet-Serret? Well, let me start out by ignoring the arc length part, and then I'll circle back around to it. This change in tangent over change in s. Well, how do I get the tangent function? That's kind of the question I'm trying to answer here. Well, the tangent, as I mentioned earlier, is just like the first derivative of f. So I can actually go up here and use this Jacobian that I talked about in the last video, right? So we have this Jax.Jacobian of the curve. Maybe I'll go ahead and just copy that code and come down here and put it in my function over here. So I'll maybe call this f, because I want to take the Jacobian of f. And I will say, just to keep the names generic, the change in f over the change in time is going to be this Jax Jacobian of f, because that's what the Jacobian is, right? It's the first derivative of a function that potentially has multiple points and multiple independent variables, or has multiple functions within it and multiple variables. So now that I have that, I can just say I want to return, to get the tangent, I just want to return the change in f over the change in time. And this isn't quite correct, but let me just cover the basics real quick, and I'll circle back around to it. Now to get this normal function, I need to do something kind of similar, but the normal is sort of like the second derivative of the function. So if I go here, I can maybe say the change in f over the change in time 2 is just Jax.Jacobian of df dt. So I'm taking the derivative of the derivative, or the second derivative, which is sort of what I'm trying to signify here. So then I will just call that, and I actually need to say I want to take the tangent at some time t, and I want to take the normal at some time t. And now, if I go ahead and run this, I shouldn't get any errors, and I think this will get me something I can kind of work with. So I'll just say maybe the tangent normal vectors are going to be equal to Frenet-Serret of the curve function, which I defined earlier. Sweet. I'll go ahead and run that. And now, let's look at maybe the tangent of point 0. So when t equals 0, what's the tangent? And it will give me an array. And this looks to be about the same as what I did before when I did this Jacobian function. So the Jacobian equals the get Jacobian of the curve. And yeah, sweet. So that's the same as what I did before. But that's not what we wanted, right? Because we didn't just want the tangent function to be returned. We want this change in tangent over the change in s, which is, yeah, a little bit more complicated than maybe what I've done already. So the change in s is a change in arc length. And if I go over here real quick, arc length, this is a really great video demonstration, I guess. Like the arc length is this theta here, and as you go through and your curve gets wider, you get to different arc lengths. And it can be anywhere, I guess, from, I guess it can be anywhere from 0 to 2 pi radians, right? Or 0 to 360 degrees. So if I were to go ahead and come back here, I need to make some changes to my Frenet-Serret. So let me, actually no, okay, I need to stay in Wikipedia for a minute. Actually, no, I'll go down to paint here. So if I go down to the bottom here, we see we already have ds, or we already have this dt, change in tangent over the change in time. That's what we've done already with Jacobian relative to t. What I instead want to do is I want to take the change in s over the change in time, so the arc length over time, and I want to like divide this ds over dt, divide the change in tangent over the change in time over the change in arc length over the change in time, and that'll give me this desired change in t over change in s. So I need to somehow get a function for ds over dt. Well, Wikipedia gives me some really great insight into how to get that. And if I go down here, it will eventually tell me, I think, something with the Taylor series. I hated that in Calc 2. But here we are. This is saying the sorry, let me take a second to breathe. I am just, I'm getting a little bit ahead of myself, I guess. This tangent function is just the derivative of my curve, so this would be an f of t, f prime of t, divided by the magnitude of f prime of t. So what is this saying? Well, this magnitude of f prime of t is actually the same thing as this arc length over time. And that's a math proof I just really don't feel I have time to get into. But yeah. So I need to take the magnitude of this function, and I need to take the magnitude and divide it by like the magnitude of itself. So, and then for the normal, I need to do the same thing, but divide it by the magnitude of the tangent function. So I guess with that, let me come up here, and yeah, sweet. So I need to define a new function for the change in arc length over time. So I will define maybe this change in arc length, ds, over dt, in terms of t, and that is going to return to me the normalization or the magnitude of the vector. So we will use jnp.linalg, so Jack's numpy's linalg module, and we will use the norm, which is the magnitude. It's what these double brackets mean. And so I will just say return the norm of ds over dt. So if I go ahead and I do that, it should work. Now tangent, I need to divide this tangent by ds dt at a certain point t. And so that is this first one, tangent, done. This normal vector is going to be a little bit different because I need to take the tangent function and then divide it by the magnitude of the tangent function. So actually, if I circle back around down here, I'm not exactly doing this correctly, I just realized. So yeah, let me just go ahead and I will copy this tangent. And so I will say define normal of t as the tangent of t divided by this linalg norm of tangent of t. And then this should give me what I am looking for. So I'll go ahead and hit enter and then run this, and I will be getting an error. It's telling me, I think this happens when I don't give it the proper, I think I need to, yeah, okay, so I need to normalize it not at a, okay, so normalization, the magnitude, that's when you take, to take the magnitude of a vector, you add up like it's like the exponential average of all the points in the vector. And so I'm not taking that at a specific point of t, I'm taking that of the whole function. So I think if I run it that way, it'll still give me an error. Well, let me backtrack for a second. I think I actually need to do this df dt squared divided by ds dt. Yeah, okay. So that's kind of what I was describing down here with the arc length. So this change in t, I guess for this case, it would be like the change in n over the change in time, and then divide it by ds over dt. So with that, I can go ahead and copy this ds dt and paste it in there. And then, if I try to run that, I should be able to run it down here, and I still get an error. This is not good. There must be some sort of issue with how I'm putting this in. So I'm taking the Jacobian of f, I'm taking ds dt, taking the tangent of at that specific point. What is it having an issue with? Oh, it's having an issue with the 6, which is when I try to take df dt. So it's having an issue up here. Do I need to take it at a certain point t? Oh, okay. Apparently I do need to take this at a certain point t. So then I can go back down here, and let me change this lineage norm. I want to take, return the tangent of t divided by the lineage norm of, so the magnitude of the tangent. So now, if I go ahead and run this, it should, yes, okay, here it is. So this is the tangent unit vector. So this is like the tangent unit vector, the normal unit vector from the Frenet-Serret formulas of curve. And this is saying that when t equals 0, the unit vector is 0 in the x-axis, about 1 in the y-axis, and about that number in the z-axis. And so that about fits with what we're doing in the curve, right? Because you know, point 0 is right here, so all the velocity should be in the x or in the y-axis. I guess this is a perfect. Let me go back up here. All the velocity should be in the. Come on. No, it's so hard to know where the screen is and where it isn't. But if you look right here, this is when t equals 0. It makes sense that all the tangent should be in the y-axis, and none of it should be in the x-axis. All the motion is in the y-axis. The z is going to be constant throughout the function. So if I were to go ahead and say, I'm going to take the tangent when t equals 1, we would see the z value is still the same. That's just a set magnitude divided by a set derivative, because it's just mz. And yeah, these are the Frenet-Serret functions. In the next episode, I will use them to calculate the surface point at a certain distance from the curve using the cross product of these two. But I'll get into that in the next episode. Thank you very much for watching, and I hope you have a wonderful day. Bye-bye.